Welcome back to my channel. Just the fact that you are here today suggests that you're already feeling overwhelmed with chemistry, and the upcoming exams are really making you fearful because I think this is one mountain that you did not prepare for the entire year to climb. So don't worry, we are still not that late. We are late, but then I think I have you covered. So, with this video, we are going back to the basics. No frills, no advanced topics, no unnecessary description of details, just focusing on the NCRE topics. Topic by topic, I'll be explaining the basics. And then from each topic, I'll be telling you what are the probable questions. You can say, a guest paper. What possible questions can you expect from each topic? And whether you just want a quick recap or you've not done anything throughout the year, I think this video is going to help all of you to build your confidence. So we can still ace the exams if you do this video carefully, clearly, take notes, go through, and spend some half an hour after the video to revise what you've done. Every day, as I post a video, you follow it regularly, and then please comment after watching the video whether it helped or not. And if you would like to have more such videos for the entire syllabus in the coming 20 days, I would like to help you. So, without feeling overwhelmed, let us start. Tame yourself, stick to your seats, open your copy, and let us start. Yeah. So, this chapter starts with the uh, mole concept, that is, starts with matter. Matter whose chemical classification is as shown. This is the chemical classification of matter. Chemical classification, mixtures and pure substances. Mixtures are classified as homogeneous mixtures and heterogeneous mixtures, and pure substances are elements or compounds. When it comes to elements under pure substances, we can talk of carbon, we can talk of oxygen. That means the atomic forms or the molecular forms, right? And compounds, something like water, carbon dioxide, glucose, etc. These are the examples of compounds. Homogeneous mixtures are those which completely mix with each other to form one single phase. For example, something like sugar and water, salt and water, substances that dissolve, right? Or maybe alcohol and water, liquids that are miscible with each other. Heterogeneous mixtures are which do not intermingle, do not completely mix with each other, but form different phases, such as sand and water, or maybe oil and water, right? So, this is chemical classification. Remember, it is classified as mixtures and pure substances. Mixtures are classified as homogeneous and heterogeneous. Pure substances is elements and compounds. One point where you tend to make a mistake, elements are made up of atoms, atomic forms like carbon, or molecular forms like oxygen, nitrogen. These are all elements or elementary forms of a substance. But compounds are made up of molecules, and each molecule is made up of more than one kind of atom. Now, what is matter? Matter is anything that has mass and occupies space. Under mixtures, what are mixtures? The main components of mixtures, or the main points about mixtures that you need to keep in mind. Mixtures have variable composition. Components retain their characteristic properties. Like, for example, if I have a mixture of, let us say, iron filings, and sulfur powder. Let us say I have a mixture of iron filings and sulfur powder. And if I bring a magnet to, let us say this is a magnet with north and south pole. If I bring a magnet closer to this mixture, iron filings are going to get attracted to the magnet, right? That means even after forming this mixture, iron has not lost its magnetic properties. Hence, mixtures retain the characteristic properties of their components. Clear? These may be separated into pure substances by physical methods. The same example I take, supposing you have iron and sulfur, bring a magnet to the surface, iron will get attracted towards the magnet, and we can separate iron, leaving behind sulfur. So, simple methods of separation can be physical methods such as evaporation, crystallization, magnetic separation, etc. Mixtures of different composition may have widely different properties. Examples: air, milk, gasoline, etc. Now, pure substances have fixed composition. They cannot be separated into anything simpler and not by any simple physical methods. Properties do not vary. Diamond, an example of element; graphite, an example of an element; glucose, an example of a compound. Each of these, now diamond will be made up of so many carbon atoms joined together, so many carbon atoms, right? So we cannot break carbon into anything simpler by simple physical methods. Similarly, graphite, this is also an elementary form. Now, glucose is made up of so many molecules, each molecule made up of so many different atoms, such as C6H12O6 is one particular molecule. So, if I have, let us say, glucose in a container, then this container is going to have so many different molecules of glucose. All the molecules of glucose. This is a pure substance made up of molecules of the same kind. But if to this I add water, that means I dissolve glucose in water, then I'm going to have so many different molecules of glucose, C6H12O6, C6H12O6, along with so many different molecules of water. So this is now, since these are going to dissolve into each other, we are going to get a homogeneous mixture of glucose in water. I hope you are clear. These are elementary forms of pure substances: diamond, graphite, oxygen, nitrogen, sulfur. All these are elements. Glucose, carbon dioxide, water, all these are compounds. But elements and compounds both are considered pure substances. Why? Because if you take any small piece of diamond or a small piece of graphite, they would be composed of same kind of substances, same kind of atoms or molecules throughout. Similarly, if I take a sample of glucose, I'll find all same kind of units in it, that is all glucose molecules. But if I'm talking about a mixture, let us say homogeneous mixture of glucose and water, I'll have two different kinds of molecules in it, glucose molecules and water molecules. So understand the difference between pure substances and mixtures. So pure substances are classified into elements and compounds as what we've discussed. Element consists of only one type of atoms, cannot be decomposed further into simpler substances. And examples of elements: sodium, this is a metallic element; hydrogen, a non-metallic element; copper is also a metallic element; oxygen, non-metallic element; similarly sulfur is also a metallic element. These consist of only one type of atoms and we cannot break it into anything simpler. That is why we consider this to be a pure substance. Next is a compound. Compounds contain two or more elements, very important, in a definite proportion by weight, in a definite proportion by mass. Constituent elements do not retain their properties. What does it mean? Hydrogen is an inflammable gas. Oxygen supports combustion, whereas when the two combine to form water, water has none of these properties. It is used to extinguish fire. Okay, so you understand, when hydrogen and oxygen chemically combine to form water, in this compound, the two elements lose their original properties. But if I just mix hydrogen and oxygen under ordinary conditions, let us say as a component of a sample of air, then we are going to call this as a mixture because they are not chemically combined. Each has not lost its property. So this composition is going to be considered as a homogeneous mixture. Remember, mixture of two or more gases is always a homogeneous mixture. Similarly, we have example of carbon plus oxygen to give carbon dioxide. Carbon dioxide is a compound. Carbon was black solid. Oxygen is a gas which supports combustion, and carbon dioxide is a gas which obstructs the presence of oxygen and hence is used to extinguish fire. Right? Oxygen is one of the requirements to sustain life, and carbon dioxide is an outcome of using oxygen to liberate energy. Fine. So they have different properties. Similarly, nitrogen and hydrogen are odorless gases. When they combine, they form ammonia, which has a specific ammonical smell. So characteristic properties of the elements is lost when a compound is formed. Mixtures are further classified into two types, as we've already discussed. Homogeneous means same composition throughout. Components are indistinguishable, that is, sugar in water. When sugar dissolves in water, we cannot see sugar molecules in that sample of water. Gaseous mixture, like mixture of gases, such as, say, let us say oxygen plus nitrogen plus even water vapor. When all these mix together, we cannot uh, distinguish simply by looking at that mixture whether it contains oxygen or nitrogen or water. Clear? So it forms a single phase. Any number of gases when mixed together form a single phase, that is a homogeneous mixture. And all soluble solids in liquid or all miscible liquids together, they all form homogeneous mixtures. Heterogeneous mixtures, as you can see here, you can see two different layers. This is one phase, this is another phase. So this is a heterogeneous mixture. Okay. Heterogeneous mixtures do not have the same composition throughout, and components are distinguishable. That means we can see two different layers. If you put oil and water, you can see two different separate layers, one of oil, another of water. So water and kerosene, again, they do not intermingle, do not intermix with each other. They are immiscible and hence heterogeneous mixtures. Now, from examination point of view, the question that you can be asked is, they can ask you to distinguish between elements, compounds, and mixtures. So here I have classified, you can take maybe a screenshot or take down notes to write down the differences between. Most of the times, a question which asks you to differentiate maybe elements and compounds or compounds and mixtures is generally a 2 marks question. And if you get a 2 marks question, that means you're supposed to give four important points. Four important points which mention a different aspect. Okay, do not use the same point and use different set of words to explain that. So element, pure substance made up of one type of atom. Substance composed of two or more different types of atoms bonded chemically, and this is combination of two or more substances that are not chemically bonded. This is one difference. This consists of identical atoms. This consists of molecules with fixed ratio of different atoms, and this contains substances in variable proportions. These substances can be elements or compounds. They can be elements or compounds, anything. Properties of elements. Elements have unique properties. Properties differ from those of its constituent elements in compounds. Properties vary depending upon the substances present. And this is another important point, cannot be separated into simpler substances, can be separated by chemical means, and can be separated physically. So any 4 points you can memorize, then we have examples to quote under each, right? Then here I have given points if they ask you to differentiate between a mixture and a compound. This is a very, very important question. Give differences between a mixture and a compound. So, four important points you can memorize. Let us say you can memorize the first one, that is constituents in any proportion, here by fixed proportion by mass. Then, second point is properties are midway between those of its constituents. That means the properties are not different. The properties of the mixture are basically similar to the properties of the components, whereas here the properties are entirely different. Then third point is separation, separated by simple mechanical means, but here cannot be separated by mechanical. We need to use some chemical methods, or energy in the form of heat or light is often required. Okay, mixtures formed due to a physical change, whereas compounds are formed as a result of a chemical change. This does not require any energy, but this requires energy in the form of absorption or evolution of light, heat, etc. Melting and boiling points are usually not sharp. So, what word can be used for melting points being not sharp? We can say the melting and boiling points are diffuse. That means they will generally have a range of melting point. Let us say a substance starts to melt at 50 degree and the melting completes at 55 or 60 degree, whereas chemical compounds possess a sharp melting and boiling point, such as if a compound has a melting point 50, the entire compound is going to melt at 50 degrees C. So if you get 2 marks question to distinguish between elements and compounds, you can use this one. You can use separation, this, and this. I would suggest out of these 5 points, memorize any four to be quoted as your answer. An example, whether asked or not, with a question, you must quote. Okay? Any kind of definition or differences, wherever examples are valid, you must quote the examples. Next topic is properties of matter and their measurement. So, what was the first topic? The impossible important question from the first topic that we've already done could be differences between elements, compounds, and mixtures, any two or all three. And then the second question is they could give a list of substances and ask you to differentiate, like which out of the following is an element and which is a compound, and which is homogeneous mixture, which is heterogeneous mixture. You can get a question of that kind. So next we come to properties of matter and their measurement. Every substance has unique or characteristic properties. The measurable properties are expressed in the form of some units. Please remember, the measurable properties are expressed by specific quantities called units. Now, properties can be classified as physical or chemical properties. Properties which can be measured or observed without changing the identity or the composition of the substance are called physical properties. Without changing the identity or the composition of the substance are called physical properties. So, what are physical properties? This is definition statements given in NCERT. Properties which can be measured without changing the identity or the composition, without bringing about any chemical change. For example, color, odor, melting point, density, etc. But the properties which can be measured or observed by a chemical change are called chemical properties, like combustibility. To measure combustibility, we need to burn the substance in excess of oxygen. Similarly, basicity. Now, international system of SI units, what you need to know here is you need to remember the 7 fundamental units, then their names and their symbols. And this is a table that you need to understand. And this is very important to learn, children, the prefixes, suffixes, and how do we read it? Like, for example, if I take here at this point, if I have a meter, okay, and all these are called submultiples, the powers which are with negative sign, these are called submultiples, and all these with the positive powers of 10 are called multiples. Multiples and submultiples. How do I read it? Some part till here. Okay. Now, understand, let us suppose we have these terms. Now, if I put a meter here and a meter here, I will read it as 10 to the power minus 6 meter is equal to 1 micrometer. Similarly, I put a meter here and I put a meter here. 10 to the power minus 3 meter is equal to 1 millimeter. 10 to the power minus 2 meter is 1 centimeter. Okay. Similarly, I put here a meter and here a meter. That means 10 to the power 2 meter is equal to 1 hectometer. Okay. If I put a meter here and here, it means 10 to the power 3 meter is equal to 1 kilometer. Fine. I hope this was understood. This is how we read this table. Clear? So must learn this table. This will help you in your easy calculations. Now, based on this table, we are going to use dimensional analysis. What is dimensional analysis? When we convert one system of units to another, that is dimensional analysis. And according to your NCRT, there's a method which is called unit factor method or dimensional analysis. This method is explained for converting one form of unit to another. Now, a unit factor, what is a unit factor? A unit factor is something which has a value equal to 1. So, if I take an example of a unit factor, let us say I know 100 centimeters is equal to 1 meter. I know 100 centimeter is equal to 1 meter. 100 centimeter upon 1 meter. Right? This is equal to 1. I just brought this right hand side as a denominator on the left hand side. I get 100 centimeter upon meter is equal to 1. Or I could have done 1 meter upon 100 centimeter. This is also 1. So each of this quantity is called a unit factor. Why this is called a unit factor? Because its value is equal to 1. Similarly, if I write, let us say, 1000 gram is equal to 1 kilogram. This means 1000 gram upon 1 kg is equal to 1 kg upon 1000 gram, and each of these is equal to 1. So each of these is called a unit factor method. Right? Okay. So continuing with an example of dimensional analysis, children, just helping you recall what is dimensional analysis method. In general, if I ask you how many seconds are there in 2 days, 1 day is 24 hours, 1 hour is 60 minutes, and 1 minute is 60 seconds, right? So converting 2 days to seconds The unit factor can be multiplied in a series in one step. Okay, how? 2 days into 24 hours upon 1 day, right? Then into 60 minutes upon 1 hour, into 60 seconds upon 1 minute. Now, what have we basically done? I have chosen this as a unit factor. 1 day is equal to 24 hours. Hence, from here, 24 hour upon 1 day is going to be a unit factor. Similarly, 60 minute upon 1 hour is also a unit factor. 60 second upon 1 minute is also a unit factor. Why are we multiplying these unit factors like this? Purpose is I want to cancel off day. This hour and this hour cancels. This minute and this minute cancels. What am I left with? I'm left with 2 into 24 into 60 into 60. Right? I'm just left with these numbers. And which unit am I left with? This one. What did we start with? 2 days. So 2 days is going to be these many seconds. What did we do? We have simply converted 2 days. We've multiplied with the unit factors till we reach to the desired unit. Okay. So this is going to be our answer. Now, similarly, this was a question we had in our like school exam in the one of the previous exams. The question says convert 2.66 gram per cc, 2.66 gram per centimeter cube, and I want to convert it to microgram per picometer cube. So what am I going to do? I'll go in steps. I know one of the conversion factors is I want to convert gram to microgram. And I know 1 gram is equal to 10 to the power 6 microgram. And children, I also want you to understand, you children commonly make a mistake between powers. You know, 1 gram is 10 to the power 6 microgram, or 1 microgram is 10 to the power minus 6 gram. This is how you are used to learning this part. Okay. So just be careful. You have learned 1 microgram is 10 to the power minus 6 gram. If I ask you 1 gram, remember it's going to be a positive power. Get the point? So the memory aid for this is, you know, out of gram and microgram, gram is a bigger unit. So a bigger unit will always have a smaller numerical value. Just remember that. Similarly, you know, 1 meter is 10 to the power 2 centimeter. If I ask you 1 centimeter, it's 10 to the power minus 2 meter. Okay. So just to test you, if I ask you, just fill in these blanks. 1 nanometer is equal to dash meter. 1 gram is equal to dash kg. 1 meter is equal to dash decimeter. 1 kg is equal to dash gram. 1 meter is dash millimeter. And 1 millimeter is dash centimeter. If I ask you to write these, you can just pause the video, write down these to test your own self. Clear? And then check whether you've written it right or not. So 1 nanometer is 10 to the power minus 9 meter. If I had asked you 1 meter, then it would have been 10 to the power 9 nanometer. Be careful, nanometer is a smaller unit than meter, which means nano will have a bigger numerical value, meter will have smaller. If I'm writing 1 with nanometer, I'll have a smaller value with meter. Similarly, 1 gram, gram is a smaller unit, so kg will have a smaller numerical value. Meter is a larger unit, so decimeter will have a larger numerical value. So just check if you've written it correctly or not. This is something very simple, but children still tend to make a mistake in this. And 1 millimeter is going to be 10 to the power minus 2 centimeter. Clear? Hope this is right. So now let us pick up the conversion values here. We know 1 gram is going to be 10 to the power 6 microgram, which means for us, the unit conversion factor method is going to be 1 gram upon 10 to the power 6 microgram. Or you might write it as 10 to the power minus 6 gram is 1 microgram. This is also fair, right? So the unit conversion now is going to be this. Or it could have been this. You can keep any one in the numerator, any other in the denominator. Basically, the ratio is going to be 1. Similarly, you could have done it like this 10 to the power 6 microgram upon 1 gram. So, what do we need to do here? I need to convert 2.66 gram per centimeter cube. First, I'll convert gram to microgram. So, how do I do that? I want to cancel gram. So, I'm going to put 1 gram here and 10 to the power 6 microgram here. What will this help me to do? This will help me to cancel gram with gram, and answer will be left in microgram. And that's what we want. Our next step is to convert centimeter cube to picometer cube. Now, what are the conversion factors? I'm going to rub this because we've already converted these into our desired quantity. And now let us pick up the next conversion. What are we conveniently aware of? We know 1 meter is 10 to the power dash picometer. Pico is 12. 1 meter is 10 to the power 12 picometer, or 10 to the power minus 12 meter is 1 picometer. And then we also know 1 meter is 10 to the power 2 centimeter, or 10 to the power minus 2 meter is 1 centimeter. We are familiar with these conversion values. Fine. What can you do? First, I can convert this centimeter cube to meter. I can directly find out a conversion factor between centimeter and picometer. But in case you are confused, you all always know the conversions starting from the base unit, that is meter, to any other unit. So what am I going to do? If 1 meter is 10 to the power 2 centimeter and I make it cube on both the sides, I get it as 1 meter cube is 10 to the power 6 centimeter cube, or 10 to the power minus 6 meter cube is 1 centimeter cube. So I'm going to put here 1 centimeter cube and 10 to the power minus 6 meter cube. This conversion factor. Why? Because my purpose is to cancel off centimeter cube with centimeter cube. I have the answer in meter cube. Next, what do? I use another conversion factor between meter and picometer. So I want meter in the numerator. I can put 10 to the power minus 12 meter upon 1 picometer. I want it as cube. 10 to the power minus 12 meter upon 1 picometer, and I make cube on both the sides. Why? Because I want meter cube. This meter cube and meter cube will cancel off. I'll be left with picometer cube in the denominator. So finally, what are the values that I'm left with? 2.66 into 10 to the power 6 into 10 to the power minus 12 cube, which will make it 36. In the denominator, I'm left with 10 to the power minus 6, and the unit left is picometer cube. In the numerator, the unit left is microgram. So when I solve, I get 2.66 into 10 to the power 6 minus 36. And this minus also goes up and becomes plus 6. So 2.66 into 10 to the power 12 minus 36 minus 24. This is the unit is microgram. The unit is microgram per picometer cube. So this is going to be our answer. So next we come to mass, weight, volume, density, and temperature. What are the important questions related to this? You know what is the difference between mass and weight? Mass is the amount of matter and weight is the force exerted by gravity. Now these two statements are more important when it comes to physics. In chemistry, these are rarely asked. The mass of the substance can vary from mass of a substance is constant, whereas weight may vary from one place to another due to change in gravity. Okay. So for chemistry point of view and questions point of view, what is important? What is the SI unit of mass? You know, it's kg. Commonly used unit, smaller unit can be gram. Apparatus used as an analytical balance. I'll put this link with this video. This describes an analytical balance. An analytical balance figure is given in NCERT. So you can be asked labeling of that analytical balance. Although it's rarely asked in theory, it is most often asked in the practical exams. Okay. So volume, what are the important points that you need to know? Volume, first, to begin with, you need to know the SI unit. SI unit, volume is meter cube. Why? Because volume is length cube and SI unit of length is meter. So SI unit of volume is meter cube. Smaller volumes are denoted in centimeter cube or decimeter cube. And very, very important point, 1 decimeter cube is equal to 1 liter. Please remember, on the decimal system, 1 decimeter, which is equal to 10 to the power minus 1 meter, and which is equal to 10 centimeter, right? This is also equal to 1 liter. Hence, please try and understand 1 liter is equal to 1 decimeter cube. Okay, 1 liter is basically equal to 1 decimeter cube. 1 decimeter cube means 10 to the power minus 1, the whole cube meter cube, or 10 to the power this, which makes it as 1 liter is equal to 1 decimeter cube is also equal to 10 to the power minus 3 meter cube is also equal to 1000 centimeter cube. And centimeter cube is also called as CC, which stands for centimeter cube or cubic centimeter. Fine. And you also know 1 liter is equal to 10 to the power 3 milliliters because milli means 10 to the power 3. Hence, 1 milliliter is equal to 1 centimeter cube. Please revise and recall these. I summarize 1 liter is 1 decimeter cube is equal to 1000 ml is equal to 1000 cc, which also means 1 milliliter is equal to 1 cc and 1 liter is equal to 1 decimeter cube. And SI unit is meter cube. So 1 liter is 10 to the power minus 3 meter cube. So all these are important units of volume. This is the apparatus that is used for measuring volume. The first one is the graduated cylinder. The second is the pipette. This is the pipette. This is the burette. And this is a titration flask or a conical flask. All this is mentioned in uh, NCRT. And this one is a volumetric flask. Volumetric flask. This is the bulb. Here, volume is written. This can be 100 ml, 250 ml, 500 ml, 1 liter, etc. And remember, a volumetric flask is used to measure standard solutions. It is used to make standard solutions. And what are standard solutions? Standard solutions are those whose concentration is known. All this is NCRT. Standard solutions are those whose concentration is known. Important questions, children. Which apparatus is used to make standard solutions? Volumetric flask. And volumetric flask has one single graduation. When you fill liquid till here in this, the total volume is going to be 100 ml or the volume that is mentioned on this bulb. Okay. Next we come to density. Density is mass per unit volume. You know the SI unit of mass is kg. That of volume is meter cube. So SI unit of density is kg per meter cube. Density is also expressed in gram per centimeter cube. This is a CGS unit. Then is temperature. Three common scales to measure temperature according to your NCRT: degree Celsius, degree Fahrenheit, and Kelvin scale. Remember, we don't put degree with Kelvin. Degree F is related to degree C according to this formula, and Kelvin scale is related to Celsius scale according to this formula. Fine. So, what kind of questions can be asked? A measured temperature on Fahrenheit scale is 200 degree F. What will be this reading on the Celsius scale? So, what are you going to do? You can just pause, try calculating it yourself, and then match your answer. What formulas are you going to use? Degree F is 9 by 5 degree C plus 32, or degree C is 5 by 9 degree F minus 32. We have been given the temperature in degree F. So what are we going to do? We want degree C 5 by 9 into 200 minus 32. Solve this and check your answer. So on solving this, you're going to get your answer as 93.3 degrees C. Coming to the next topic, scientific notation. Now, what is scientific notation? What you have to remember is scientific notation is generally used if you are asked what is the significance. It's used when one has to deal with extremely large numbers or extremely small numbers. So we take them to the powers. In what form do we express them? Scientific notation is n into 10 to the power n, where n, this is called the digit term. This varies between 1.0 to 9.999. Okay. N is any exponent having a positive or a negative value. For example, if speed of light is 3,0,0,0,0 and 3 zeros meter per second, then the scientific notation is going to be 3 into 10 to the power 8. What did we do? We simply placed a decimal at this point. After one non-digit, non-zero number, we'll place a decimal and then 1, 2, 3, 4, 5, 6, 7, 8. 8 places after this, right? So 3 into 10 to the power 8. This is 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros. So we're going to put it as 10 to the power 8, right? This is called scientific notation. Remember, we always convert a number to first decimal place. Supposing I ask you to convert this to scientific notation, you're going to put a decimal here and take the values to a power of 10. Similarly, if I'd asked you to convert 0.0310 to scientific notation, you will be moving the this decimal 1, 2 places to the right. So the number will become 3.01 into 10 to the power. Since you move the number to the right, you'll have a negative power. When you move the number, the decimal to the left, you moved 1009 means you have a decimal here. You have moved it 1, 2, and 3 places to the right, so you had a positive power. If you move the decimal to any number of places to the right, it will be a negative power. I give another example. Supposing we had a number 409083. So we assume the decimal to be here. If I have to move this decimal to 1, 2, 3, 4, 5 places, 5 places to the left, that means I'm going to place a positive power. Okay, so this is how we write scientific notation. Next is uses. We can use scientific notation in these mathematical conversions like addition, subtraction, multiplication, and division. So under addition, what do we do? Supposing we have to add these two numbers, the first thing is we will try to make the powers the same. So how do we make the powers same? Supposing we have this number and this number to be added, what are we going to do? In order to make powers of both same, this is 10 to the power 4, we will make this also 10 to the power 4. How do we do that? If I move this decimal one place to the left, I'll have one more positive power here. So this number will become 0.895 into 10 to the power 4. Okay. So I will bring both the powers same and then take the power as common. 10 to the power 4 I'll take out as common. I'll be left with 6.25 plus 0.895. When I add these two numbers, I'll be getting 7.545 into 10 to the power 4. Right? So, in a nutshell, to summarize, the method to add is make the powers same and then add the numbers. Clear? Same rule will be applicable for subtraction also. Supposing I have to subtract these two numbers. I have to subtract 2.5 into 10 to the power minus 2 minus 4.8 into 10 to the power minus 3. Again, what will I do? I will bring this to this side, 0.48. Since I've moved it to left, that means I'll have one positive power and 10 to the power minus 3 is already there. So these two will become 10 to the power minus 2. So the number that I have now, 2.5 into 10 to the power minus 2 minus 0.48 into 10 to the power minus 2. I'll be taking 10 to the power minus 2 common, 2.5 minus 0.48, and I get this as the answer. This is how to do addition and subtraction using scientific notations. Okay, now multiplication and division. For this, this is very simple. Simply multiply the numbers 5.6 and 6.9 and add the powers. Right? And supposing I ask you to express your answer in scientific notation, you will move this digit, this decimal one place to the left, which means you'll have one positive power. 10 to the power 13 is already there. So scientific notation expression is going to be 3.864 into 10 to the power 14. So I hope this is clear. And now express the following in scientific notation. You can pause and you can practice writing these, writing in scientific notation. So the answers, first, I am going to assume decimal here. So 1, 2, 3, 4, 5 places to the left, a positive power. So 1.86 into 10 to the power 5. This is 4.07, 007 in 10 to the power 3. Check your answer and give marks to yourself. Next is 6.8 into 10 to the power minus 3. 700 is going to be 7 into 10 to the power 2 and 7.0042. This is already scientific notation. So in case I want to express a power of 10, I can put it as into 10 to the power 0. Yeah. So the next is significant figures. The next topic is significant figures. Significant figures are, what is the definition of significant figures? All the meaningful digits which are known with certainty plus one unknown digit. So significant figures are all the meaningful digits which are known with certainty plus one uncertain digit. In general experimental measurements, we have two terms used: precise measurements and accurate measurements, right? So, what is the difference between precision and accuracy? This is one important question for your school exams. Differentiate or define the terms precision and accuracy. So, remember, precision reference refers to the closeness of various measurements for the same quantity to each other, right? Supposing a value is 2, let us say 2.5. A given value is 2.5. So a student takes values as 2.8, 2.4, 2.3, 2.3, and 2.4. So we would say these are precise values. They're close to each other. Okay. So precision means closeness of the various values to each other. But in case the student had taken values for a value whose length is 2.5, if a student takes different measurements repeatedly and finds the different values as 2.2, in the next measurement he calculates this value to be 2.6, in the next measurement he measures it to be 2.8, we will say these values are not precise. They have low, the student has low precision of measurement. Okay, because the values are far from each other. So precision means closeness of the various measurements of the same quantity to each other. Accuracy is the agreement of a particular value or average value of various measurements to the true value. So if I take the average of these values, I'm going to get 2.533. The original value was 2.5. So I would say the measurement is quite accurate because of the closeness of the average to the true value. So it has a good accuracy, but bad precision because the various measurements are away from each other. But in case somebody had taken measurements as 2.4, 2.5, 2.6, the average of these would have come out to be 2.5. So these would have been precise because they're close to each other. Plus the average is close to the true value. Hence, we would say this measurement set is both accurate and precise. So I repeat, children, please remember, precision is the closeness of various measurements of the same quantity to each other. Whereas accuracy is the agreement of a particular value or average of various measurements to the true value. I hope this is clear. So what is the importance of significant figures? Uncertainty in experimental or calculated values are indicated by significant figures. Okay. What is the meaning of uncertainty in measurement? Let us suppose I give you an example. If you are taking reading from a graduated cylinder, a measuring cylinder, right? And let us suppose you are measuring this value. And in case your eye level is here, you're going to get the correct value. But in case your value to be noted is here, and you are looking at this value this way, or maybe you have to take this reading and you're looking from this value. Both these green and yellow readings are going to have a parallax error. Yeah, because the right rule says you must look at a reading at eye level with the reading. So this is going to be the correct measurement, but both these measurements are going to have some error, some uncertainty in measurement, which is called as parallax error. Okay, so every measurement is associated with some kind of error. If we show it with this dart game, then this is the target, and all the three arrows are hitting the target. So this is accurate as well as precise. This hit here, this is the target, right? The three are close to each other, so this hit is precise, but this is not accurate because it is quite away from the actual value. Again, this is the target, so these three are far off from each other as well as from the target. So we will say these are neither accurate nor precise. Now, if a question is asked, true value is 2.00 gram, measured value by student A is 1.95 and 1.93, and measured value by B student is 1.94 and 2.05. By C student is 2.01 and 1.99, right? If I calculate average here, 2.01 plus 1.99 by 2, I'm going to get the average as 2. In this case, 1.94 plus 2.05 by 2. And here I'm going to do 1.95 plus 1.93 by 2. I'm going to get the average as 1.94. In this case, I'll be getting 1.995, right? So this value is going to be what? Both accurate as well as precise. Why accurate? Because this value is closest to the original value. And these two values are close to each other as well. So accurate as well as precise. This value is precise. These are close to each other, but not accurate because this value is very far off from the true value. And measured by student B, we say this value is quite accurate because of closeness of this value to the true value, but it is not at all precise because the two values differ greatly from each other. I hope this point is clear. So what is the answer? Answer C. That means student C is both accurate as well as precise. So for your school exam, one of the possible questions is differentiate between precision and accuracy, and you will simply write the statements that we've done. So another question is again a previous year question we had in one of our school exams. Two students performed the same experiment separately. One of them recorded 2 readings of mass. Each one of them recorded 2 readings of mass. Correct reading of mass is 3 grams. On the basis of this, mark the correct option. So again, you can pause and just think of the answer and then check your answer for this. It's the same as what we've done just now. So the answer for this will come out to be B part. Results of student A are both precise as well as accurate. Why? Because the average of these two is going to come out to be 3, which is same as the given value, and the two values are also close to each other. So they are precise as well as accurate. These two are far off from each other as well as the average is going to come out here to be 3. So this is going to be accurate. B is going to be accurate, but not precise. Fine. Whereas A, the average is going to be 3, and the two values are close to each other. So this is going to be both accurate as well as precise. Hence, the answer is going to be B part. So these are the important questions related to precision, accuracy. Now we are coming to rules for determining the number of significant figures. Rules for determining significant figures, all non-zero digits. Like numbers 1, 2, 3, 4 onwards till 9, they are significant. For example, 285 centimeter, this is 3 significant figures. Zeros preceding means coming before. Zeros preceding means coming before. The first non-zero digit are not significant. For example, if we have the number 0.03, this has one significant figure, which one? Only this one. Because zeros preceding, that means lying before, the first non-zero digit are considered to be not significant. Similarly, this is going to have two significant figures, only these two. The next rule says, zeros between two non-zero digits are always significant. So 2.005 is going to be 4 significant figures. Both these zeros are going to be considered to be significant. Similarly, the number was 20101. This also will have 1, 2, 3, 4, 5, 5 significant figures. We're going to count both these zeros under significant figures. Even if we had a number like 3.0000003, any number of zeros, all the zeros between two non-zero digits are all counted as significant. So this number is going to have 3, 3, 6, and 1, 7 significant figures. I hope this is clear. Next point says zeros at the end or right of a number are significant. At the end or right of a number are significant, provided they are on the right side of a decimal point. For example, 0.200 is going to have 3 significant figures, these ones, because they are after a decimal. If a number ends in zeros that are not to the right of a decimal, the zeros may or may not be significant. Very important point. 1500 gram has 2 zeros. Will they be significant or not? They may or they may not be significant. For example, 1500 gram, if I'm measuring using some balance with which I can measure least value of 1 gram, right? Then this is going to have 4 significant figures. But if I have measured it with a balance which can measure to a least of 10 grams, I don't have a weight smaller than 10 gram, right? That means this place is going to become insignificant. I will be able to change only this place. So I will be having 3 significant figures in this value. Clear? This is less chance of being asked at the school level. So, but if you can understand, you can do this too. Otherwise, just remember, children, in order to specify the number of significant figures in such a quantity, what do? We express it in scientific notation. How do we express it in scientific notation? If I express 1500 as 1.5 into 10 to the power 3, when I multiply this, I'm going to get the answer as 1500 only. But writing it like this means it has only 2 significant figures. Why? Because the exponential value does not count for significant figures. This has 1.5 means 2 significant figures. So this expression is going to show only 2 significant figures in the quantity. But if I write it as 1.50 into 10 to the power 3, it means it has 3 significant figures. Because we've just done the rule, all the zeros that are to the extreme right and after a decimal point are considered significant. So this number is also going to be 1500, but this expression shows that this has 3 significant figures. Similarly, if I write it as 1.500 into 10 to the power 3, so this time it is going to have 4 significant figures, right? But if nothing is mentioned, I just ask you 15, this is very important, children, this is very important, can be asked at the school level. If I just ask you 1500 gram, I don't give you scientific notation, I don't give you any specification about the balance used, then your answer has to be 2 significant figures. Then we are not going to count these zeros which are given without a decimal point. I hope this point is clear. So if I ask you how many significant figures in 800, you would say 1. If I ask you in 800 meter, you would again say 1. Is it right? But if I say 800 dot meter, now it becomes 3. If I say 800.00 meter, now it becomes 5 significant figures. Please be careful. Whether it's a pure number or it's a measurement without a decimal, we do not count the zeros unless and until some specification is given. So this particular slide is very important for you to know, and children generally have a confusion in this. Now, lastly, maybe emphasize that exact integral numbers or counting numbers. Counting numbers means 2 balls, 20 eggs. These have infinite significant figures. Why? Because we never make mistakes in counting numbers. 2 balls will be counted as 2 by everyone. 10 pens, nobody will count these as 11 or 12 or 9. If somebody counts them that way, that's a blunder. That's not precision. Okay. So what is precision? Like supposing I have a value, I have a reading here, and this is 2, this is 3. Now some might count this as 2.3. Some might consider this as 2.4. Some may take it as 2.2. So this second decimal, this place is going to be uncertain. This will be certain. So we are going to say this is 2 significant figures. But in case I'm counting something as 10 pens, then 10 pens can be expressed as 10.0, 10.00000, any number of zeros, which means this has infinite number of significant figures. There's basically no error in counting numbers, pure counting numbers. So any of these pure counting numbers will have infinite significant figures. Okay, how do we deal with significant figures while doing addition and subtraction? Please remember, very simple, very important point to understand. While adding, the answer has to be reported to least number of decimal places. That is, least number of digits to the right of a decimal point. For example, we have these 3 numbers to be added, and I want the answer to be reported to the correct number of significant figures. What am I going to do? Just do the simple addition, and the least number of decimal places are 1. I'm not going to count significant figures. For addition and subtraction, we only count the least number of decimal places. So the least number of decimal places are 1. So I'm going to round off this answer, this final answer, to 1 decimal place, not significant figure, but 1 decimal place, which means my answer is going to be 31.1. This is done for addition and subtraction. And for multiplication and division, we are going to report our answer to least number of significant figures. No more significant figures than the measurement with the fewest significant figures. So if I look at this number has 2 significant figures, this number has 3 significant figures. So I'm going to report my answer to 2 significant figures. So I'll be rounding off this answer. 3.1 will be the answer. I'm reporting it to 2 significant figures. Now, what are the rules for rounding off? We are going to study ahead. Rules while rounding the numbers. The digit on the extreme right side, that is the last digit of a number, may be removed by rounding off. For example, it's 1.386. I want you to express this number to 2 decimal places. That means I need to remove this number. And in order to remove this number, I'll have to increase the previous number by 1. So how do we do that? Let us go through the rules. The rules say if the digit to be removed is less than 5, then the preceding number is not changed. For example, if I wanted to convert this 4.334 to 2 decimal places only, I would drop this number. Since this number is less than 5, I would let the preceding number remain the same. But supposing the number was 4.336. So to drop this number, I would have to increase the preceding number by 1. If the last number to be dropped is less than 5, leave the preceding as such. If it is more than 5, increase the preceding by 1. If the digit to be removed is 5, then the number is not changed. If it is an even number, but increased by 1 if it is odd. For example, 6.35. I want to drop 5. The previous is odd, so it is increased by 1. Here, the last is 5. Previous is even. I leave it as such. Okay. Now, what is the purpose of this kind of conversion? The purpose is to average out the results. When we are rounding off, we don't want the original value to undergo any change. So we round off by taking to the next number in case it's odd, and in case it's even, we keep it the same. Purpose is the average result remains the same. So as an example, express the following in scientific notation. Again, pause and then write down. So this one written in scientific notation. I want you to write this to 4 significant figures. So to 4 significant figures means I need to drop this. What am I going to do? If this number after 7, the first number is more than 5, I drop all these and increase the previous by 1. The question is express the following in scientific notation and express up to 4 significant figures. So drop all these numbers and increase the previous by 1. Okay, and here also, what are we going to do? We are going to drop all these numbers because I want 4 significant figures. I need to drop all these since this number is less than 5. So I'll be dropping all these without changing this number. This number remains 32.39. What is the sum of these two? And report your answer to the correct number of significant figures. Now, sum means we have to add. And what did we do? While adding, if you give this answer, children, you get no marks because you're not studying in 5th, 6th standard where you're learning addition. We are supposed to express our answer to the least number of decimal places. And what are the least number of decimal places in this? 2 decimal places. Remember, we are not going to count significant figures while taking sum, only the least number of decimal places. So the answer here is going to be 3.39. Why 3.39? Because this 8 will be dropped. The previous will be increased by 1, 3.39. What will be the significant figures in the reported answer? So now look at this. If this is asked in exam, this is also one of our previous year papers. Reported answer of this. What are we going to do? This is all division and multiplication. And you know, while multiplying and dividing, we need to report our answer to least number of significant figures. This number has 5 significant figures. This number has 4. This has 2. And this is a pure number. Children, a non-decimal number is considered to be a pure number. And this number of significant figures in this are not counted while deciding our result. So we will not look at, we will use this number while doing the calculation. Like we are going to multiply these 2 numbers and then divide with these 2 numbers. But while deciding significant figures, we will not consider the significant figures in this. So out of this and this number, 2 is the least number of significant figures. So our reported answer will also have 2 significant figures. You don't even need to calculate. If the question is asked this way, what will be the significant figures in the reported answer? They've not asked you the reported answer. So you'll simply say because the least number of significant figures are 2, so the answer here is 2. Now after this, we come to laws of conservation. So we will continue with this in the next video.